Hello to you. I'm Jessie Johnson. This is mathematics, science, basics of first order exponents and second order power to a power exponents and exponentials. The definition of an exponent for algebra is 1. A symbol, which can be a number or other symbol, standing as an example of something placed at the upper right of another base symbol to show how many times the base symbol is to be multiplied by itself, increasing it by large amounts. Number 2, a rate of growth which is equal to itself as a base. Number 3, a base quantity multiplied by that same base quantity one or more times. There are two orders to exponents and exponentials, first order and second order or power to a power. Each order has two levels. The first order has level 1, exponent notation, and level 2, exponent operations. The second order has level 1, exponent notation, and level 2, exponent operations. Exponent notation with several basic operations will be shown. Exponents include 1. Exponent functions, simple and complex. 2. Exponent constants. 3. Exponent integrals. 4. Exponents of time. 5. Exponents of matrices. 6. Exponents of distributing. 7. Exponents in power expansion. 8. Exponents in output. 9. Exponents in matrices. 10. Exponents in groupings and sets. 11. Exponential curves. 12. Exponential growth. 13. Exponential polynomial time forms. 14. Exponential operations of addition, subtraction, multiplication, division, reduction, and 15. Algebraic forms, etc. First, a few base rules, then first order exponents and a few of its base rules, then second order exponents or power to a power and a few of its base rules, then a few examples of each will be shown. Hold on please, I'm going to move the camera. Now to continue. Basics. Exponent rules. This is general. Number 1, any number can be used as a base and raised to a power. Number 2, 1, O-N-E, 1 to any power equals 1 when multiplied but not added. 3, 0, Z-E-R-O, 0 to any power equals 0 when multiplied or added. 4, math is shorthand and uses symbols in place of words, sentences, phrases, and paragraphs. 5. The operation multiply has two meanings. 1. Shorthand addition, and 2. Shorthand but non-addition. Number 6. All exponents have a base and an exponent as at its upper right. Number 7. There are two types of exponents. 1. First order exponents and second order power to a power exponents. To continue, we'll go to 8. Only specific second order exponents can be reduced to a first order exponent. Number 9. All operations can be done on first order exponents, but all operations cannot be done on second order exponents. We'll continue now. First order exponent rules. I put 2 of them. Number 1, all first order exponents have one base and one exponent. Number 2, all operations can be done on first order exponents. We'll go to second order exponent rules. Second order power to a power rules. Number 1, number 1, 2 or more bases and 2 or more exponents may be used in second order exponent power to a power. Number 2, in all second order exponents, all bases and exponents are sub-bases and sub-exponents except the first base and the first exponent. Number 3, all sub-bases and sub-exponents expresses how many places or place factors are present. Example, 10 to the 6th power, 2 10 to the 6th power equals, when expanded and written out, 1,000,000 to the 6th power, which equals 10 to the 6th power, its first place, times 10 to the 2nd power, its second place, times 10 to the 6th power, its third place, and so on, all the way to 10 to the 6th power, which is its 1,000,000th place, equals x. A second example is 100 to the 28th power, 2 10 to the 12th power, 2 10 to the 12th power equals 100 to the 28th power, 2 10 to the 24th power, which equals 100 to the first place times 100 to the second place, and so on to 100 to the 28th place equals x, and which equals x to the first place times x to the second place, all the way to x times x, all the way to 10 to the 24th power place, equals k. Now we'll go to number 4. Examples of sub-bases and sub-exponents is such as 10 to the 6th power, which with 10, in this case, the base is the first base. The 6th power here is an exponent, therefore it is the first exponent. 2, the 100 to the 100th power, 100 in this case is the first sub-base, and to the 100th power exponent, 100 exponent here, which is the first sub-base, pardon me, the first sub-exponent, first sub-exponent. 2, the 5,738, this is the second sub-base. 2, the 76,492nd exponent power, which is the second sub-exponent. 2, the 18th, which is the third sub-base. 18 to the 10 to the 3rd power, which is an exponent, which is the third sub-exponent. 2, the 807,319. 2, the 5,926,817 power. Now 807,319 is the fourth sub-base, and 5,926,817 power as an exponent is the fourth sub-exponent. 2, the 10 to the 35th power. In this case, 10 is the 5th sub-base, and 35 is the 5th sub-exponent. And it is continued on the next page. Continued here on the next page. Continued all the way to 10 to the 10th to the 6th power, which is, this 10 is the 6th sub-base, and this 10 to the 6th power is the 6th sub-exponent. 2, the 10 to the 10 to the 10th 7th power. 10 right here is a base. It is the 7th sub-base, and this here, 10 to the 7th power here, is the 7th sub-exponent. 2, the 100 to the 10 to the 3rd power, which is the 8th sub-base. This 100 here, 8 sub-base. This 10 to the 3rd power is the 8th sub-exponent. 2, the 100, which is a base, to the 10 to the 100th power. 100 here is the 9th sub-base, and 10 to the 100th power of it is the 9th sub-exponent. 2, the 728, which is the 10th sub-base, to the 750,896 exponent, which is the 10th sub-exponent, to the 1587 exponent, which is the 11th sub-exponent. Now we'll go to number 5. Number 5, the second order has one sub-base and or one sub-exponent at a minimum. Number 6. The second order exponents can be reduced to first order exponents in most cases. Specific second order exponents. Only specific second order exponents can be done this. Number 7. The second order exponents are indefinite second order exponents if they cannot be reduced. Number 8. Second order exponents can end with or without a sub-base or a sub-exponent. Second order, number 9, second order indefinite exponents cannot be reduced to a first order exponent and cannot be worked out because the number of subs are almost infinite or too large for brain or machine. Algebraic symbols can be used in some places, but it can never be known in quantity. Now let's go to first order exponent operations. A, multiply 2 to the third power times 2 to the fifth power equals 2, where you add the exponents. 3 plus 5 equals 2 to the eighth power. 5 to the fourth power, first worked out, then you put it to the third power equals 5 to the fourth times 3 equals 5 to the 12th power. We'll go to B. On dividing exponents, first order exponents that is, 8 to the 7th power divided by 8 to the third power equals 8, where 7 minus 3 equals 8 to the fourth power. 6 to the second power divided by 2 to the third power equals 6 to the second power equals 36, 2 to the third power equals 8, equals 4 and 4/8, which equals 4 1/2. Subtract 3 to the fifth power minus 4 to the third power equals 243 minus 64, which equals 179. When you add exponents, first order that is, you have 4 to the second power plus 9 to the second power equals 16 plus 729, which equals 745. When you work these out, negative exponents, which is E, which is such as 4 to the minus second power equals 4 1/2, which equals 1/16. Minus 15 to the third power equals minus 15 times minus 15 times minus 15, which equals 3,375. Minus 1 to the 12th power equals 1 when the exponent is even number. Minus 1 equals minus 1. Oops, I forgot to put it, but nonetheless, it's like 27 goes here. 27 minus 1 to the 27th power equals minus 1. It becomes an odd exponent because you are using an odd number. We'll go to F. 4 with an exponent of minus 1 equals 1/4. We'll go now to first order operations, first order exponent operations, such as, first order exponent notation. This is 10 to the 6th, 10 to the 3rd, 10 to the 7th, 10 to the 34th power, 6 to the 928th power, 2 to the 106th power, 8 to the 10th power. B, 100 to the 100th power, 7 to the 29th power, 10 to the 29th power, 756.8 to the 5th power. This is the first base. The first base, this is the first exponent. 10 to the 90th power. C, 10,000 to the 200th power. This is the first base. This is the first exponent. We'll go to D. 10 to the 6th power equals 10 times 10, 10 first place times 10, second place, all the way up to 10 times 10 to the 6th place equals X. 10 to the 3rd power equals 10 times 10 times 10, or 10, which is the first place, 10 times 10, which is the second place, times 10, which is the third place, equals X. We'll go to E. 986 to the 4th power equals 986. This is the first place, times and so on all the way to times 986 to the 4th place equals x. Now we'll go to F. 473.8 to the 38th power equals 473.8, which is the first place, times 473.8, which is the second place, all the way to 400 times 473.8 to the 38th place, which equals x. Now we'll go to second order exponent notation, which is power to a power. This is notation. We'll start with A. 100 to the 10th power, 2, 10 to the 100th power. This here, 100 is the first base. This one here is the first exponent. This one here, this 10 here is the first sub-exponent. This one here is the first first sub-base. This here is the first sub-exponent. We'll go now to this one, 100 to the 2600th power. This one here is the first base. This one here is the first exponent. To the 10 to the 6th power. This here is the first sub-base. This here is the first sub-exponent. We'll go to B. 10 to the 60th power. 100 to the 87th power. 1529. To the 12,296 power. To the 10 to the 6th power. To the 921 to the 201 power, to the 100, to the 10 to the 100th power, and that means this 10 is the first base, this 60 here is the first exponent, this 100 here is the first sub-base, this exponent here, this base is the first sub-base, this exponent here is the first, this is the first sub-exponent, this one here is the second sub-base. This one here is the second sub-exponent. This one here is the third sub-base. This one here is the fourth sub-exponent. This here is the, fourth sub-base. This one here is the third sub-exponent. This one here is the fifth sub-base. This one here is the fourth sub-exponent. This one here is the sixth sub-base. This one here is the seventh sub-base. This one here is the fifth sub-exponent. We'll go to E. We'll go to C. 10 to the 3rd power, 2, 10 to the 6th power, 2, 10 to the 18th power, 2, 57 to the 337th power, which is also raised to 10 to the 7th power as an exponent itself, equals 10 first place times 10 second place times 10 third place equals x, which is to the 10 to the 6th power, which equals x, which is equal to x, which is the first place here, times x, which is the second place, all the way to x here, which is the 1,000,000th 10 to the 6th power place. And it is continued over here, where x to the 100th power, where x is x exponent 100 to the 18, which is to the 18th power, which equals x, which is at the first place, times x, which is at the second place, and so on to times x, which is at the 100 to the 18, which is to the 18th power to itself place, which equals x, to the 57 to the 333rd power, which is raised also to the 10 to the 7th power, equals x, which is the first place.
Do you mind if I used your pen?
Go ahead. First place times x, which is to the second place, times x to the third place, times x to the fourth place, and so on, times x, which is to the 57th power, which is to the 57th base, 333rd power, with the 333rd power raised to the 10 to the 7th power place. Now we'll go to second order exponent operations, power to a power. Operations, not notation, but operations. We'll start with A. 10 to the 6th power, 2 10 to the 6th power equals 1 million to the 1 millionth power. This is expanded. We'll go to B. 100 to the 100th power, to the 1000 to the 8th power, to the 10th to the 39th power, to the 100 to the 10 to the 10 to the 758th power, equals, this is reduction and reducing it, equals 10 to the second power times 10 to the second power to 10 to the third power, which is raised to the 8th power, and so on, to 10 to the 39th power, to 10 to the 107th power, and the 39 and the 107 is added. 39 plus 107 equals 146. Now, to the 10 to the second power, to the 10 to the 758th power, which equals 10 to the second power, raised to 10 to the second power, then to 10 to the third power, which is raised to the 8th power, to 10 to the 146th power, which is the 39 plus 107, equals 107, and continued to 10 to the second power, to 10 to the 758th power equals x. This is how you reduce a second order to a first order. Now we'll go to C. Indefinite second order exponents, power to a power, indefinite second order exponents. This is where 10 to the 6th power, 210 to the 30th power, 210 to the third power, which is 100 to the 70th power, 250 to the 7015 power, and so on, where it has no symbol, none whatsoever. This cannot be reduced. Now we'll go to this one. 10 to the 80th power, 10 to the 400, 2 10 to the 8th power, 2 10 to the 450th power, 2 10 to the 9th power, which is raised to 100 to the 23rd power, 72 to the 9,008th power, which equals infinity minus 1. This one is an indefinite second order exponent. It cannot be reduced. 10, we'll go to the last one. 10 to the 39th power, 2 10 to the 37th power, to 10 to the second power, which is raised to the 28th power itself, and to 7,385 raised to the 7,385 to the 7,096 power, which is raised to 10 to the 4th power itself, equals infinity. This cannot also be broken down to a first order exponent. I want to thank everyone for listening and watching, and have a very good day. Please share this video on sub-exponents and first order exponents and second order exponents, or power to a power. And we will meet each other on the next wonderful video, and have a very, very fine day.